Our first speaker is Diego Matias Cazon Tejerina. He's a local, and he's going to tell us about ADS CMT, thermal and quantum phase transitions and self-duality. Please go on.
Good afternoon to everyone. Today, the short talk, I want to talk about how geometry computes transport. And this is part of the program of ADS-CMT. We will see certain systems that have thermal and quantum phase transition. And we will see how a Boehly coupling gamma tunes a BKT-typed critical temperature. The Boehly coupling is, okay, a quick intuition about it is just a curvature electrodynamic coupling or corrections to our system, while the BKT comes from Berezinski-Koterlitz-Thouless lines, and it comes in certain materials in two-dimensional, and they are from topological phase transitions. So that's the roadmap, and we will work in this strongly coupled regime where we can find certain materials that comes here are the strange metals that they are near critical points of certain materials, like for example in the right, in the picture of the presentation, we can see the phase diagram of a high TC superconductor. There we can see how, while putting chemical doping, the ferromagnet gives a way for a superconductor and a strange metal regime. In this regime, we have a strongly coupled regime where we don't have long quasiparticles. Here, the optical spectra is broad, and that means that our typical models like Fermi liquid or Boltzmann or Drude fits not longer applies. So we need something that doesn't assume quasiparticles, but it still gives us the conductivity, the susceptibilities, or when a phase transition turns on. So from here, we need to have a non-perturbative tools for this transport, and we get an idea to take this condensed matter system and maps to a gravitational one in one dimension higher. That's the idea, that we take our model in a curved space-time, solve the wave equations, for example, and get transport there. That's the leverage that we will use for superconductivity in a moment. But first, let me explain a bit of ADS-CMT and the dictionary of it. In ADS-CMT, we have a book geometry that is the curved background that we will use. We have an horizon that will arise a temperature in our system. The condensed matter system lives here in the boundary of the theory. There we can put certain fields, like for example a bulk gauge field. The bulk gauge field encodes the conserved current, and the behavior near the boundary are here, for example, the non-normalizable mode is the chemical potential, while the normalized mode is the current density of the condensed matter system that lives in the boundary. While the bulk scalar encodes the order parameter operator of our system. To get transport, we need retarded functions or retarded Green's functions. So we need to put ingoing boundary condition at the horizon of the black hole, and via Kubio formulas, we get the transport phenomena that we want. And also, we can take the radar coordinates as an energy scale, the renormalization group scale of the theory. So near the horizon, we have the infrared, while more on the boundary, we have the UV, that is the ultraviolet part. So that's the dictionary of the ADS-CMT, and we can take it for study holographic superconductors. That is a model for high TC superconductors. In the holographic superconductor, we will work on a black hole that can be Schwarzschild or Reisner-Nordström. We will take Reisner-Nordström because a certain mechanism that is important, but everything that we need is in this action. The action has two fields, a gauge field that is for electromagnetism, while another scalar field that is for the condensed system. And also we have the part that is Einstein in ADS. The above, okay, we need to work on, as I said, in a black hole that will give rise a temperature. Above this, a critical temperature, we have that the scalar field is 0, so we are in the normal phase, while below TC, we have that the horizon grows a hair, so that goes to a condensed phase, that is our order parameter. The mechanism that I was talking about is the near horizon ADS2 cross R2 of the Reisner-Nordström. I mean, the Reisner-Nordström near horizon has this geometry, and in the geometry, this lowers the effective mass of the scalar field. And when this mass of the scalar field crosses a certain bound, that is a BF bound, we get an instability. This is the growth of the hair. So we have, when we cross for this of this bound, we get the condensed phase of the system. For conductivity, we perturb the gauge field, and via Cover formula, we get the following, where these coefficients comes from the, as I said, comes from the gauge field behavior near the boundary, that are the following. The first one and this, and the second one. And to the last model that I was talking about, that is the minimal holographic superconductor, what we want is to put a correction, a value correction, but it's not arbitrary. It has many interesting facts around the higher derivative theory of Einstein equations, and it encodes string effects, it's consistent, but we will take the phenomenological part of this correction, and it's because it breaks electromagnetic self-duality. What does it mean? It means that the conductivity will have this particle vortex asymmetry. So for certain values of the gamma coupling, for example, for greater than 0, we have that the conductivity has a Drude-like peak. That means that the transport is mainly from particles. That is the particle channels, while the contribution in the gamma less than 0 comes mainly from the vortex channel that is a deep in the conductivity profiles. But, okay, we can have also another intuition to get more into this correction, and it's the top-down motivation. This Velasco coupling can be seen as a gravity dual of an so-called EBGM model. And in the EBGM model, we can have a certain truncation, a consistent truncation that goes in the infrared effect as an effective field theory of a Landau-Ginzburg theory. That means that the gravity dual, that is the Velasco coupling, goes to a certain relativistic Landau-Ginzburg model. Okay, first we have that gamma is greater than 0. Okay, gamma has particle channel on one side, vortex channel on the other side, and also we have from duality of a top-down model, we have a relativistic Landau-Ginzburg. So that points directly to something that is more deeper, like a transition between them. So that's the idea. That's why we want this Velasco correction. So that's the intuition that we have for the project, and we will take this minimal holographic superconductor in a Reisner-Nordström black hole for the ADS4, and put it this Velasco coupling. We will analyze this new gamma that is the scaling dimension of the scalar field, and also we will study the critical temperature, also the optical transport below the critical temperature, and of course these are the parts that we want at the beginning of the theory, and in fact we can get it. and it's a critical temperature goes as with a BKT scaling that comes from the ADS2 of the theory. Also, we see the particle vortex asymmetry on the conductivity, and it matches the electromagnetic duality that we expect at the beginning. Okay, we zoom this here. We zoom near the Reisner-Nordstrom black hole, and we have this ADS2 cross R2 throat, and here the scalar field behaves as a certain coordinate with the following exponent. This exponent is important. This is the scaling dimension of the scalar field, and the scaling dimension of the scalar field of our theory. When we put the gamma, it deforms this scaling dimension, and it is important because we have a mechanism when we take for certain values of nu that are less than 0, okay, greater than 0, the scalar field is stable, but for lower than 0, we have this violation of the BF bound that I said at the beginning. So we have a transition in the phases. So, and what type of transition we have? Not a mean field transition, instead a BKT transition. Since we deform this nu in our theory, it also gives a rise a transition with gamma as a noob of it. And okay, in our theory, since we deform, but by this Boehly coupling, we have that the mass square, we have the charge and the current density. We have that the Boehly coupling renormalize this coupling with this coefficient, and this is the BF threshold defined, this critical surface. And as I said, gamma renormalize this critical temperature. And all of this lives in the infrared of the theory. Since we are near horizons where we have this geometry of ADS2, near IR, that is the regime that we have this kind of behavior of the critical temperature. Let's see the phase transition. The phase transition on. In fact, we have that the order parameter profile here. In fact, we have that the gamma coupling is perturbing the profile of our condensed matter system, and here we have two plots. In the minimal holographic superconductor, we can choose between two types of quantizations, and each of them will arise to a certain profile of the transition. But here we have that. For gamma equal to 0, we have the following profile, while for gamma greater than 0, we have the following, and that's the idea that gamma shifts TC, and it modifies the near onset slope. And also we can find the behavior of the real component of the conductivity. Here we have that these are two plots, one for each quantization, and for each plot we plot these different temperatures, and this one is near critical temperature. What is the main thing that we find? That here near when we have the IR of the theory, I mean infrared, that is low omegas, low frequencies, we have this small dip of near TC, and also we can have this small peak, and that's that I was talking about at the beginning, that we have this Drude-like peak and this dip, Drude-like dip, that comes from the particle or the vortex channel in our holographic superconductor. So near horizon, at low frequencies, and that is the regime of infrared, we have these signatures of the Boehly coupling, and we can't relate them with the BKT type critical temperature that we find at the beginning. Okay, at the last. slides. So what we get in this project is that, okay, a clean map from a non-perturbative transport we get from geometry to Cuba, and we studied transport in a strongly coupled system. Also, we find that the Boehly coupling, in fact, gave a rise to a BKT-type critical temperature, and also this particle vortex asymmetry on the theory. And that's all. Thanks.
Are there questions?
And so I'm not familiar with the formalism and the model, all of that, but I got curious on why, I don't know, you call this the BKT scaling. I didn't see why and how.
Yeah, in the papers that I found, they just take the BKT type scaling because we have this exponential fall off of the theory, so we have this type of scaling, right? But you know, this is more like a model. So in fact, to have a real BKT type line is more difficult since we are translating too many things into simple things. So okay, we can take it like from the XY model, right? But we are kind of trying an effective field theory for it. That's why we are taking more phenomenological things more than the XY model for it. But here we have also these particular vortex things. But okay.
More questions? You have?
In geodesic solution, particularly, which parameter gave you that TC?
What?
In that geodesic solution, particularly, which parameter gave you that TC? I mean, how did you get that?
In the I don't know.
TC.
In the TC.
Critical temperature, yeah.
You mean in this TC?
Yeah.
Which parameter from where this comes from?
Yeah, yeah.
I mean, okay, the exponential behavior comes from, okay, we take the scalar field on this curved background. In this curved background, okay, since we have, it's like have Klein Gordon in a curved space. So we get like a Schrodinger equation for it. In this Schrodinger equation, we have certain parameters. So we get a quantization for it that are called the Efimov states quantization. And we get like logarithmic oscillation of a logarithmic scales. We take certain boundary conditions, and we get this type of scaling. And that's why ADS2 is important, because just in ADS2 we have this type of scaling because of the boundary conditions and also the behavior of the scalar field on this Schrodinger equation on ADS2.
More questions? I also have a question. These holographic superconductors, they were a hot topic 15 years ago. So what is the status of if they exist or they don't, I mean, in the real world?
Okay, if they come on, okay. There are many models for holographic, for high TC superconductors. This is just one. And we have many hints that this, in fact, model a high TC superconductors, but they are still there, you know, in effective, like constructing an effect, something more real. But this is just one of the models that study holographic, high TC superconductors, and we can say that gives kind of better agreement with experiments than the typical BCS, let's say. But, you know.
Well, thank you, Yogo. Let's thank again. So the next speaker is Miradel Seifi Mirjafarlou.
Good afternoon, everybody. Today, I would like to talk about the explicit Pfaffian expression for Fermionic Gaussian states and operator beyond the computational basis. This presentation is the summary of the two following works, which the first is explicit Pfaffian formula for amplitudes of Fermionic Gaussian pure states in arbitrary Pauli bases, and the other is matrix elements of Fermionic Gaussian operators in arbitrary Pauli bases, a Pfaffian formula. First, I'm going to talk about the properties of these Fermionic Gaussian state and operators. Then I'm going to also introduce them, and how to write them in also in the computational and alternative basis. Also how to write the Gaussian operator in computational or alternative basis, and how to compute the post-measurement entanglement entropy in transfer field Ising chain. Okay, Fermionic Gaussian state and operator are among the earliest and most widely studied many-body fermionic system with application spanning a range of fields. They describe a wide range of physical state, including ground and thermal state of free fermionic Hamiltonians like XY, XX Ising, XXZ chain, which they can be mapped to free fermionic Hamiltonians via Jordan-Wigner transformation, or approximation to the ground state of the interacting fermions. Their study dates back to the early days of quantum mechanics with the introduction of Hartree-Fock-Bogoliubov variational techniques, which enables us to minimize this quantity by the state psi. They are also playing an important role in the impurity problems, and also valuable in quantum simulation and modeling the time evolution of the free fermionic system after a quantum quench. While properties of fermionic Gaussian states and operator are well understood in the standard computational basis, a major challenge persists in the determining their amplitudes or matrix elements in arbitrary Pauli basis, which the spin representation can be achieved via the Jordan-Wigner transformation, which is a method to map a fermionic operator to a spin and vice versa, which can be mapped as these equations, which means that one can write the Gaussian states in the sigma z basis by just these two substitutions. When fermionic Gaussian state and operator are expressed in the computational basis, their amplitudes or matrix elements corresponds to the Pfaffian of specific submatrices or Pfaffinus of an antisymmetric matrix. However, in spin system, alternative Pauli bases often offer more pertinent information, and computing these amplitudes and matrix elements in this basis is valuable for various applications in quantum physics. For example, if we consider this if we consider this RC being in the computational basis, by multiplication of this unitary matrices on this state, one can find the states in the in arbitrary Pauli states, which we show it by phi theta alpha, and the matrix elements can be found by multiplication of this unitary U and U dagger from the left and right. But the problem with this, it's like the size of the state, it grows exponentially with the size of the system, and we are looking for an efficient way to how to find it. And these unitary matrices are by giving this equation, and for an example, when the phi theta alpha is like these values are corresponding to the sigma x and y basis. By computing now these amplitudes and matrix elements, one can find the probabilities of being spins in any desired configuration in any basis, which we know as a formation probability. And this formation probability can directly apply to measure post-measurement entanglement entropy, global entanglement in fermionic Gaussian state and operator, founding Shannon-Renyi entropy and doing like a tomography of Gaussian states. One can define any arbitrary Gaussian pure state can be defined as follows, which there is like normalization, and this A, I, and AJ. Oh my God. This A, I, and AJ depends on this configuration, can be creation or annihilation operator. And the Gaussian operator can be defined as follows with satisfying the following properties. Now, how we can write these Gaussian states in computational and also in alternative basis? It is demonstrated that in this reference, one can find the Gaussian pure states in the computational basis by this equation, which there's like normalization, a sign factor, and a Pfaffian of like submatrices RIC, which RIC is the submatrices of matrix R, by obtaining just like removing some rows and columns. And the sign factor by giving this equation, and this PF denotes the Pfaffian, which can be defined for 2n by 2n antisymmetric matrix by this equation, and which has this following properties. Pfaffian A squared, it's equal to determinant of A. These are like some examples when it's like L equal 2, the Pfaffian of this matrix can be given by A12, and regardingly for the L equal 4 can be given by this equation. Now, how we can compute this Gaussian states in alternative basis in a more efficient way? If we consider Gaussian states, pure states with L qubits, the amplitudes of this configuration S, which each Sj is in the basis phi j, theta j, alpha j, the amplitudes can be found as this equation, which there's like some phase, sign, and a normalization, and a Pfaffian of a matrix, which the elements of this matrix can be given by this equation, and also with these conditions, which I'm not going to enter. And how about like Gaussian operator? How we can write now the Gaussian operators in computational and alternative basis? If we define the computational basis state I like this, and also the dual state J as this base state, and also we consider, if we consider I1 as I and I0 as a complement of I, and the same for J, one can show, we show that one can write the Gaussian operator in the computational basis by this equation, which just there's a sign factor, determinant of T, 2, 2, and Pfaffian of a matrix, which the A can be given by this equation, which is 2L by 2L matrix, and the X, Y, Z can be found from the following, as follows. So how about to finding this Gaussian operator now in an alternative basis in an efficient way? If we define the dual state S and the state S prime as this, which S prime, we consider S prime, S plus and S prime plus as a set of qubits with spins up, and the S minus and S minus, S prime minus as a set of qubits with spin down, and with associating this +1 for the plus and -1 for the spin down, one can find now the Gaussian operator in the, oh my God, the Gaussian operator in the alternative basis, which we show by phi theta alpha in a, as this equation, which there's a sign factor and also the Pfaffian of a matrix, which the elements are also by giving this equation, and they're just like some sine cosine, and like the rest like depends on the configuration S, and we found that this A matrix can be given as before, and there's just like another antisymmetric matrix, sigma and sigma prime, which they produce a sign factor, and that means the entire is all plus or minus 1, which can be given by these two tables. Now, how one can measure the post-measurement entanglement entropy in transverse field Ising chain? If we consider a bipartition of a system into two subsystems A and B, which the A is like A1 union A2 and B equal to B1 and B1 union B2, and by performing a projective measurement in this subsystem B, we can study how the entanglement between the subsystem A1 and A2 depends on the distance between separating them. So we define the Rényi entanglement entropy as this equation, which the alpha is the Rényi index, rho A1 is the reduced density matrix of subsystem A1, which can be found as doing partial trace over the subsystem A2 of this quantity, and the states Psi can be given by this equation, which we found this A is the amplitude in the phi theta and alpha basis, and this is just the formation probability of subsystem B, which can be given by sum over the subsystem A of the whole formation probability of the whole system, which can be simplified as this equation. Like that. Anyway. Now, to place our funding, we use the two key results from the conformal field theory applied to critical spin chain with the short-range interaction, which this result describe the scaling dimension of the post-measurement entanglement entropy and the behavior of the decay exponent eta as a function of the Rényi index alpha, which can be given by this equation, which D is the distance between the subsystem A1 and A2, which also follows these properties, and the eta k can be given, eta alpha can be given as this equation, which the delta 1 is the scaling dimension. Now, the critical transverse field Ising chain, which the Hamiltonian of the transverse field Ising chain can be given by this equation. We compute the entanglement entropy for as a function of the distance between the subsystem A1 and A2 for the different values of the alpha, and for the system size of 800 by doing the projective measurement on the subsystem B being in the basis, both being in the basis Z. And we studied our results fits with the conformal field theory, and by fitting this data, one can now find this scaling dimension for this basis in the sigma Z basis. We can do the same, but with difference that we can do the projective measurement in the sigma X basis, and again for different values of alpha and different. Now theta is pi over 2 because it's in the sigma X basis, and the system of the size for the system size of the 100, and we summarize for different measurement output the scaling dimensions delta 1, which we summarized here for like being this measurement output of like B1 and B2 being in the different bases. And there are like some extra information which we extend the amplitudes formula even for the odd case, and we found the recursive formula for amplitudes, and also we found the alternative formulas for the amplitudes, and also that applying this also formula for some specific quantum system is also naturally next step. Thank you for listening, and
are there any questions? Okay, yeah.
Thank you for the talk. I had a simple question. Why do you want to change the basis? Because I think that the easiest way of working with Gaussian states is using this symplectic algebra. I think it's the easiest way of working with Gaussian states. So why do you want to change the basis?
The idea is like we already studied how one can measure like these stuffs in the standard computational or sigma z basis, and maybe someone wants to find these measurements in another basis, in any basis. So that's the reason we studied this, to find like this formula in any arbitrary basis, so that we can like apply this, so we can apply for any quantum system and study it in another basis, not only in the computational basis.
Yeah, but if you change the basis, the Hilbert space can increase faster, for example, compared with the symplectic algebra. This is
yeah,
only
but
n by
as
n.
I mentioned, like, yeah, it grows exponentially when you do that. When you like, I wrote here with the U matrix. When you multiply this U matrix with the system of the size, the system of the like this states increase exponentially. But we found a efficient way to calculate these stuffs in the other bases, so it doesn't increase exponentially in this point.
Any more questions? Questions? Okay, so let's thank again, Miradel. So the next speaker is Pedro Sanchez Farinas from IFSC USP, effect of dissipation and disorder in systems with two order parameters and continuous symmetry.
Okay, okay. Hello, everyone. The title of the presentation actually changed. So I'll talk about the effects of disorder and dissipation in the nematic phase transition of the J1, J2 model. It's the same idea. So, and the title is also kind of misleading because we are actually interested in this action here, which is more general than the J1, J2 model. It describes a system with two order parameters which couple to each other in a way to respect the lattice symmetries. In this case, is the square lattice. This kind of action appears in the study of iron-based superconductors when you have this kind of competing orders in the system. And what we are interested in here is to study the effects of disorder and dissipation in the system in a non-perturbative way, like using renormalization group techniques. So, because it's hard to study the effects of disorder directly in the action, we take a step back and study it on the Hamiltonian. This Hamiltonian is one of the models which can be described by that action of the first slide. So this is the J1, J2 model. It's just a Heidelberg model with interactions between first and second neighbors. This model has two phases, basically. The first phase is when J1 is larger than 2J2, and it's just an antiferromagnet. It's not really interesting for us. What we are interested in is in this phase here. This is the so-called order by disorder regime. And here what happens is that the lattice splits into two sublattices, the red one and the blue one. And the energy here is independent of the J1 coupling here, which is the coupling between the first neighbors. So the ground state is independent of J1, meaning that it's independent of the relative angle between the spins. So we have this huge O3 degeneracy here, which is related to the fact that the ground state is independent of the relative angle between the spins of the two sublattices. Oh, this wasn't supposed to be here yet. Just ignore this part here. Let's focus on this one. So what happens when we consider quantum fluctuations about this ground state? These quantum fluctuations will lift this degeneracy with the O3 degeneracy, and what remains is a Z2 degeneracy, which is associated with the symmetry between the x and y directions of the lattice. So the corrections due to fluctuations goes as minus cosine square of the angle between the spins of the two sublattices. So the system will minimize its energy by going into one of these two states here, which is the 0 pi and the pi 0 one. The 0 pi is the one where, actually it's changed here. It's supposed to be, well, the way I wrote it here, the 0 pi will be an antiferromagnet in the x direction and ferromagnet in the y direction, and the pi 0 is the opposite, right? So we can associate an order parameter here to this Z2 vestigial order, which is just the scalar product between the two spins of the two different sublattices. Now, what happens when we consider the effects of disorder? Well, when we add disorder to the system, now all interactions are random variables, like J1, J2 are all random. So these two states now don't have the same energy, meaning that the disorder it explicitly breaks the symmetry between x and y directions of the lattice. Therefore, this disorder will break the symmetry, but it will break it locally. In each plaquette, it will choose between the states of smaller energy, right? So this, if we write that in terms of the order parameter here, this explicitly symmetry breaking is done by a field, conjugate field to the scalar parameter, to the scalar order parameter here. So if we write down the field theory for that model, what we have to do now in the presence of disorder is to consider a random field that couples to this vestigial order parameter here, which is the nematic order parameter. So now we have this term here, which is a random field term coupled to this order parameter here. And we also have random mass, which appears when we consider a disorder system. And to actually introduce this psi here to our field theory, we perform the Herbert-Stratonovich transformation. Then we integrate out the M fields because we are interested in the nematic phase. So these magnetic fields here are not necessary for our description. And because we are interested in the effects of disorder and dissipation, we just include this Landau damping term. For now, we are including it by hand, but this kind of term appears when your system is coupled to other degrees of freedom, like electronic degrees of freedom. So it's pretty reasonable here to include them. When we do this, we get this field theory here for the nematic order parameter. But this effective field theory that we got is associated with this effective Hamiltonian, which is just a transverse field Ising model. Now with a longitudinal field, this is the random field term, which is important. And where each spin couples to its own bed of harmonic oscillator. So this is kind of a Caldera-Leggett way to introduce dissipation. And we can go from here to here. So this is our effective theory for the nematic phase. So as we reach an effective theory, which is a random transverse field Ising model, I'll just talk about the random transverse field Ising model without the dissipation and without the longitudinal fields. So the physics of this model is described by the distribution probabilities of these couplings and these transverse fields. We can have different phases here. For example, when all the H's are larger than all J's, we are in the paramagnetic phase. When all H's are smaller than all J's, we are in the conventional ferromagnetic phase. The interesting phase here is when these two distributions overlap. So when this happens, we are in the so-called Griffiths phase. And it's the phase where you can have these so-called rare regions. So these rare regions are arbitrarily large regions of the system where the system is locally ordered in a different way from this bulk. So for example, here, the bulk would be a paramagnet, but you have these large regions, which are really rare. That's what it's called, rare regions, right? Where the system is locally in a ferromagnetic order. So the effective dynamics of these rare regions here is just the dynamics of a two-level system. All the spin tunnel coherently here. Because the dynamics of these rare regions is just the dynamics of a two-level system, and we are talking about the dissipative two-level system, I'll show here some results about the spin boson model. So this is the spin boson model. It's just a spin coupled to a best of harmonic oscillators. And you have this quantum fluctuation term here. So the effect of dissipation in our system is to compete with quantum fluctuations. And this can be seen here. So the spin here is coupled to the harmonic oscillators in a way that every time that the spin flips, it has to drag all these oscillators from x0 to minus x0. So effectively, these oscillators make the fluctuation really harder. And the question we must address is which effect dominates. And we can answer this question by using a technique called adiabatic renormalization. And in turn, it depends on this parameter here called the dissipation strength, which is defined from the spectral density of the bath. It's just like the spectral, well, it's a spectral density. And what it turns out that it has a phase transition here. So for alpha larger than 1, the dissipation wins and the spin actually freezes. So here, the spin freezes and there is no more quantum fluctuations. And for alpha smaller than this critical value, the spin keeps fluctuating. So how this translates to the rare region dynamics, right? Here, the rare region, as I said, is just like a two-level system, but it's a dissipative two-level system. And what we can show using the strong disorder renormalization group is that the effective bet coupled to this rare region is actually the sum of each individual bets that compose it. So the effective alpha here is the alpha of all the spins composing the rare region. And as these rare regions are arbitrarily large, it will certainly be larger than the critical value. So these rare regions in the Griffiths phase will freeze. But now we also have the longitudinal field. And also using the strong disorder renormalization group, what we can show is that effective longitudinal field that this rare region fills is also given by the sum of each individual field. And this will be non-zero. This will be a random variable, random non-zero variable. So each rare region will align in a different direction. This wasn't supposed to be here either right now, but okay. So if we look to this phase diagram here, this is the phase diagram without disorder, all in 0 temperature. So we have this anti-ferromagnetic phase and this triporder phase, as I said in the first slides. Now, when we include only disorder but no dissipation, what happens is that disorder kills this nematic phase here. And this is due to this really nice argument due to Imre and Ma, which basically prevents long-range order for dimensions smaller or equal to when you have this discrete symmetry order parameters. So disorder without dissipation just kills the nematic order. But now when we include dissipation, we have this kind of intermediate phase here where we have no long-range order, but we have these clusters, these nematic clusters, which are all in random directions. So that's basically our main results so far. This is an ongoing work, so yeah. Basically, we got this result where each rare region freezes in one different direction. So this is a new phase of the system, which only appeared in the presence of disorder and dissipation together. And the next steps here will be, we'll do some numerics just to I forgot the word, verify these results. So yeah, that's it. Thank you.
Okay. So you already got your beer, right? You still have questions. Good.
No, I didn't get the beers yet. Yeah, thanks for the talk. So when you said you have only these two magnetic orders, is that because you restrict yourself to these one-dimensional or like order parameters that transform like a one-dimensional representation? Because in some of the square lattice, like the iron-based, you can also have these spin vertex vortex
Oh yeah,
orders.
we are not considering that. We are only looking to the nematic one, to the scalar one. So
okay.
Yeah.
Okay, thank you.
There was another one right there.
Thank you for the talk. Is this some kind of explanation? Like somehow I understood that your rare region, it's like frozen, and go back, go further. I mean, there. Every time you analyze it, you see something different, but it's frozen.
Yes.
It's like the concept of spin glass.
I don't know how to answer that, but it's not exactly a spin glass. I'm actually looking into it now, but it's a little different. So that's all I can say to you, but yeah.
It's suspiciously...
Yeah, it looks like a spin glass, but the answer is I don't know, so yeah.
Okay.
More questions? So at some point, when you started, you had the J1, J2, and then you put a disorder on them, right? Mm-hmm. So what kind of disorder you put on them? I mean,
I made both J1 and J2 random variables. So now J1 and J2 are both random.
So the range of these things are going to matter, right? So yeah. If you change the range, so in this case, you are picking what kind of? Yeah,
they are all positive. I'm supposing they are positive, but the values are not really important here. They all flow to the same distribution.
Why not important if actually, because of those two conditions that you had, if J1, I think one of them twice more than the other one, right? Right. Something like that. So you say that if the J1 and J2, they go from 0 to infinity, it doesn't matter.
No, they are just random variables. Yeah, they must be positive, but the range.
That's the only condition.
Yeah, yeah.
Okay. And then you map this to a field theory by the symmetries.
Yeah.
And then you kind of knew that there is another model which gives the same kind of field theory, and then you forgot the original one, and then you started working with the one that you actually knew about it, right?
Yeah.
And then was it like possible to actually, in each step, know that what you are actually doing in the original model that you were interested in?
Like go step by step? Yeah, it is. It's kind of complicated, but we can do it because we know what these easing spins are. They are just the scalar products of the two the magnetization of the two sublattices. So the order here would be like something strange, where you got these rare regions which are the scalar product of the spins, but they change together in the lattice, but you don't have any long-range order. If you look to the original spins, they are like all paramagnetic, but if you look to the scalar product, they are like flipping together. It's kind of that.
Let's thank again. So the next speaker is Simon Boehly from Heidelberg University, Germany, probing universal relaxation speed in a Bose-Einstein condensation far from equilibrium.
Yeah, exactly. So hi, I'm Simon. I'm actually still a master's student in Heidelberg, and I'm presenting what I'm doing in my master thesis. So as the title suggests, it's about relaxation of a Bose-Einstein condensate, which is brought far from equilibrium. And it's not about generally relaxation, but it's relaxation through a so-called non-thermal fixed point. This is a framework which is used by a few people in Heidelberg. And first, I kind of want to motivate what it is. Well, luckily, Subir already talked a bit about RG, so I don't have to say much about it. So basically now we know all this picture, this framework in which we describe phase transitions by these flow equations. And yeah, so the idea is that we can understand fixed points, or well, map critical points, fixed points, and properties which emerge here are universality and self-similar scaling. So why am I saying this? I'm saying this because they are relevant for this framework of non-thermal fixed points, which is essentially a framework to understand dynamics starting from a far from equilibrium state. So how does this work? Okay. So essentially the idea is when we start from a far from equilibrium state, what can happen is that we relax through this so-called non-thermal fixed point. Now what does this mean? Essentially means that in our relaxation, we can observe universality, as we can already see a bit here, like we can start from different initial states, we can have different parameters. However, eventually relaxation will lead through the same point, and from this on it's universal, because, well, then it's the same state. And so there's the universality part, and then there's like the self-similar scaling part. The observable that, well, I'm interested in is like this momentum distribution here. So the idea is that the momentum distribution, momentum occupation scales in this self-similar spatio-temporal fashion. So we have two scaling exponents, alpha and beta, in time, and like this function f, which is kind of describes the general shape of the this nk. So this is, well, it was a very quick rundown of this general framework. I want to precise a bit, make more precise what exactly we're looking at. So, as I said before, this appears like the scaling form. And so in this process that we are looking at, which is like so the Bose-Einstein condensate, which is brought in a far from equilibrium state, for example, like by initializing it in this like hard cutoff state. So what we can see is this kind of dual cascade mechanism. This is actually a mechanism which is quite well known in turbulence. And there the idea is that we like inject energy as a scale, and then we observe two cascades. So first of all, particle number cascade to the infrared, and then an energy flow to the UV, because, well, we have a closed system, we have particle number conservation, energy conservation. So we have these two different regimes. What we are interested in discussion is the infrared, which takes quite a simple shape. So we have this plateau until this scale k lambda, and after this becomes a power law. And this is also like the function which I'm using to model it. It's not too important. I think the important thing right now is just to say, okay, we have this kind of k lambda scale at which like the behaviors change. Okay, so like generally this is a framework that a lot of people work with in Heidelberg, well, not a lot, but a few people work with in Heidelberg. And so as I said before, I'm dealing with relaxation. So the question is now a bit, okay, based on this scaling behavior, on this non-thermal fixed point behavior, how can we extract something like a universal quantity describing relaxation? I want to motivate the motivation a bit. I want to motivate the definition a bit here. So the idea is if we restrict to the zero mode, which is essentially our condensate, and for which we want to define the quantity describing relaxation, we see the scales like t to the alpha, meaning, well, if just to 1 over alpha, we have this Now, if you want to define a quantity, something like a relaxation speed, and it should be universal, then, well, it should better be constant. So there's a bit of motivation of saying, okay, hey, let's just take time derivative of this. Now, this is like the full expression with constants, which I don't want to talk much about right now. But yeah, the important part is now that, like, heuristically, we have this definition. Now, if we do a dimensional analysis, like expressing the quantity through like characteristic length and time scales of the system, we see that we have something like this, which on its own is not very interesting. However, in like the non-formal fixed point that we're working with, we have this scaling exponent of beta equals 1/2. If we plug it in, we see that we get NA to the power of 0. So, well, I don't know, maybe it seems not too interesting so far, but the idea is more, okay, we motivate this kind of quantity, which, so like this D is the central quantity which I'm investigating, this kind of relaxation speed, let's call it. By having like a simple, let's say, naive analysis, it suggests that it should be universal in the sense that it doesn't depend on microscopic parameters like density or S-wave scattering length. So yeah, like, let's see what actually comes out of this, if like it really is universal. So what motivated my master thesis is actually this experiment that was done by Hatzi-Babic. And by the way, like, they also did this whole discussion of how to motivate and define the D. So everything I said before was not my work, it was their work. But yeah, so like they also tackled this, like defined it, and then wanted to extract it experimentally. So, well, I think it's really very fast. So this is the idea of the experiment. So then they have like a cylindrical trap, initialize the Bose-Einstein condensate in a far from equilibrium state. Like, again, since they want to kind of see if it's universal, if it's, let's say, robust, they have to use different initial states, different parameters. So that's what I do. They run experiments for different states. This is also a bit of the idea that, like, they start with different initial states, but after some time, they eventually become the same state. And then, I mean, from this point on, of course, then it's universal because they evolve the same way. And yeah, this is some more of this. These are basically their results. So they have these are experimental results of how they measure the D for different initial states, for different microscopic parameters, N and A. And you can see that, I mean, it's quite robust. Of course, it's not perfectly on D equals 3, but like, oops, that was, at least, I mean, you can already see that it seems quite robust. So that's already quite interesting. And basically, this paper in which I do it was the motivation for my master thesis, in which I'm basically first, well, I'm doing simulations, which are supposed to like reproduce their results and extend it. So yeah, maybe to say again, they did find this somewhat, let's say, universal or at least robust value of D, and now I kind of want to, well, recreate it through simulations. I want to extend the results. Maybe like I can find like boundaries of this behavior where like it breaks down and it's not universal anymore. And yeah, maybe of course can understand what's going on. So for the simulations, I describe my system, the Bose-Einstein condensate, through the Gross-Pedelsky equation. And then like numerically, I implement the time propagation using this split-step Fourier method for, yeah, since it's quite efficient. And I'm like running the whole things on GPUs on a cluster in Heidelberg, which luckily we have some A100s where it's quite fast, so it's quite fast to get some results. And well, as mentioned before, like I'm checking different initial states, different parameters, just to see like how robust this really is. I'm skipping like more details of the simulation. If you're curious about it, I have some backup slides about it. But yeah, these are essentially my results, like reproducing the experimental results. So I literally took the experiment 1-to-1 in my simulation, took like the same trap, the same numbers. And I mean, so this 3 was measured experiment. And I mean, like, so my measurement, like the simulation results are actually quite close to it. Like, we do have some outliers. That was a bit of a problem that the simulation inside the trap were quite noisy. So going to higher A was a bit of a difficulty. I'm currently working on making it a bit less noisy. So I don't have too many data points, but overall it seems to be quite in good agreement with the experimental results. And like, if I would leave out the outliers, also like the error bars would be much smaller. So this was for the trap simulation. Then I also ran some simulations using periodic boundary conditions, because then it's much smoother. I can probe like a much larger parameter range, and this is shown right here. And so yeah, as you can see, I have many more points. Overall, so also in this kind of simulation, we also see this, let's say, universal robust behavior. Okay, I have some outliers, but overall it's quite robust, which is nice. There are two striking differences. On one hand, like this value of D is now 4 and not 3, which I'm currently quite puzzled by. I still have to figure out what's going on there. And one other very interesting thing is that I actually see like this regime for low A in which like this universal property breaks down. So that was actually quite nice. So because this somehow extends the experimental results, so only more or less constant D, but I actually also find a regime in which it is not universal, but first has to saturate and then becomes universal. Okay, so maybe to recap the simulation results. So results inside the trap, so which are like 1-to-1 from the experiment, agree nicely with the experimental results. And also in periodic boundary conditions, I find universal regime. Still, this D has a different value, which I have to clarify, and I find this non-universal regime. Okay, now like to the last part. So basically, after doing all the simulations, I kind of wanted to understand what's going on from an analytical point of view. So to do this, I'm basically describing my system through this quantum Boltzmann equation, where I here basically describe how like each momentum mode changes through like this scattering expression. And well, this T matrix is essentially like, it's basically the strength of the process, which is actually quite important, and I'm going to talk about it in a moment. And yeah, what I'm using is an approximation for large occupation numbers, since I'm in infrared, and well, I'm observing the relaxation into the infrared, so yeah, the numbers will be large. So yeah, as I said before, like this T matrix is quite crucial, because that's where like this universality in the analytic approach comes from. So I'm using a result of a former PhD student from the group I'm working in. He used also like some, as we heard yesterday, like this kind of 2pi Schwinger-Keltisch large N expansion formalism, which I'm not, I don't know too much about, but so yeah, but yeah, like it was developed and already produced results. So I'm basically using now this result to describe my system. No, it's not. Okay, no. So yeah, exactly. So this is like the interaction that I'm using. And well, now one can already kind of like suspect where this kind of universality comes from. The idea is a bit that like in this expression, so this pi for large A values is going to become very large. So essentially the larger G pi will be larger than 1, drops out, and then the G drops out. And it's a bit like the idea of like how analytically we can get to this universality, so to this physics which is independent of the interaction strength. So yeah, and to compute C, basically plugging in the scaling form and then isolate C, since like the equation is nonlinear, and then I can relate it to D and extract my D. And again, like a remark, so I'm already assuming the scaling form. So like for this analytical approach, the question I'm asking is rather, okay, so let's say we are already at this non-trivial fixed point. Let's say we already have the scaling behavior. Like, what value of D is possible? So like, yeah, that's essentially the question I'm asking. And of course, then also if the D is universal, if it depends on anything or not. How much time do I have left? Okay. Okay, yeah, then I'm going to go quite fast. So the idea is, okay, like this, I can do a long calculation, arrive at this expression, and basically like there's like this dimensional integral I kappa, where like we have some integrand, the effective coupling, and that's basically where like the whole potential universality lies inside. So I can do a plot. Oops, okay, this I'm going to skip. So I can do a plot which compares our simulation results with the analytical results. And yeah, like we can see that the behavior is shown quite well. So the dots are the simulation results for the periodic boundary conditions. And the blue line is the analytical result, and we see that, well, I mean, the shape works well together. We can really see how we have this, like, let's say, universal regime where the coupling or well, the whole integral saturates, and hence also like this desaturates. And even this regime in the beginning for law A, where it's increasing, is also reproduced quite well. There's just one maybe not so small problem, is that like here, for this nice plot, I had to rescale the axes. So the axes, basically for the simulation results, to make them fit with the analytical results, on the x-axis was a factor of 1.4, which kind of makes sense because, well, to make them into one plot, I had to extract this p lambda from my simulation data, which is a bit noisy. So it's not, I suppose not too bad that there's a, well, I mean, it's factor order of 1. However, on the y-axis, I had to introduce this factor of basically 54. So there's definitely something not quite clear yet. What I at least think is quite interesting, that like this approach for this Boltzmann equation can really reproduce this like universal regime, but also this onset regime of this behavior. Well, however, I still have to clarify why there's such a discrepancy between the y values. And yeah, that's basically it. So I think it's basically what I said all. So yeah, like simulation results fit well with experimental. Yeah, like analytically, I mean, I get the right shape, and on the x-axis, right behavior, just there's like this global factor, which I still have to understand where it might come from. And yeah, I mean, I did some 2D simulations, which, well, yeah, I will not go into it. I think that's pretty much the important thing I had to say. Yeah.
Are there some questions? Yes. Well, she just was like 0.1 second.
If I understood well, this is a velocity for like how long the system it's going to the relaxation state. This is somehow related to the butterfly velocity of spreading of information, like.
What is the butterfly velocity?
It's related to how measure how you can have like a scrambling or a propagation of information in some systems. So I think it's like sounds like related, but in the otherwise like it's not relaxing, so it's going in the other direction.
So I know, like in the experimental paper, they basically call this whole process like spreading of coherence. For them, it's basically like, so I call it now here relaxation speed. Yeah, they saw it more on the experimental side as spreading of coherence, and they also compared this like a bit to how was it called, some bound leap bound for.
Yeah.
So like they didn't say it's the same. I can maybe check the. Yeah, so yeah, in this paper they kind of compared it to like this. How much it's connected, I don't know, but yeah, could be something in this direction.
Okay, thanks.
Okay, so my question is more related to the experiment. Like, do you know if they can arrive at the weak coupling regime that you arrive in your simulations to see the non-universal behavior?
That's a good question. I was also wondering if, you know, like, of course, like now simulations, there's this new regime, so it would be interesting to see if it's really the same as in the experiment, right? This I don't know, actually.
Okay.
Yeah.
I was just wondering, because maybe it does, I mean, what you're observing in your simulations is something that the experimentalists could not observe because they were not like in that regime. So
exactly, yeah.
Okay. Thank you.
More questions? So I have a question. So regarding the initial states, I mean, what are your initial states? Because ultimately, initial states should make a difference, right?
Yeah, so I have, so basically, they were inspired a bit by the experimental initial states. These are the experimental, so they are using these 3 initial states. So far I used 2 different initial states, like a hard cutoff. And so, well, I mean, yeah, well, this is of course not a hard cutoff, but like I'm using a hard cutoff state, so I take basically constant occupation until a cutoff momentum, and then I cut it off, which is, I think, quite used in like among the people who are working on it to get like this thermal fixed point, non-thermal fixed point behavior and this thing. And the second one I use is basically inspired by this experimental state, which is just like a linear decrease in log-log space.
So in a sense, do you have some sort of intuition that what kind of overlap these initial states they have with your Hamiltonian of your system?
So you mean with like the non-final fixed point state? Or?
Yeah, so somehow, you know, you also have this scaling behavior, right? Mm-hmm. And then with my simplistic field theory kind of mindset, normally if you want to have something like scaling behavior, you shouldn't have overlap with some states in the middle of your Hamiltonian. Otherwise, it's hard to see some universal, at least field theory kind of universal things.
Okay, so like this, of this point, I haven't thought much. Yeah, I mean, what I can definitely say is that, I mean, what's interesting, at least for the choice of initial states, that like the closer they are to this like intermittent state, which is close to this scaling behavior, like so the more similar they are from the get-to-go, the faster it will be. So this is one of the non-universal parts of the whole process, that different initial states need a different time to reach this scaling behavior. So yeah, there's like this non-universal onset time, and there it depends on which states they are, and like the closer they are, the more similar they are to these scaling states, the faster they reach the state. Like, for example, like this state will reach the scaling faster than this one because already it looks more like this mental distribution. But yeah, as I don't know, like generally, I think what like most people always use to see this kind of behavior as the hard cutoff state is kind of like the go-to that people use. But yeah, I think.
Another question is that that alpha and beta that they were like, are there some possibilities that they might have some sort of anomalous dimension kind of, not mean field kind of scaling too? I mean, are there some possibilities?
I mean, what I definitely know is that like we observe different alpha and beta. So first of all, they are like connected in the infrared by particle number conservation. So generally you have like alpha equals 3 beta. So generally it's just like one independent scaling exponent. I know like one person from my group has also observed like this kind of non-anomalous non-fixed point with like a beta of 0.2. By like this, like let's say the Gaussian non-final fixed point, so the standard, so to say, has 0.5. If there are like small deviations from the 0.5, this I don't know. I think maybe the difficulty for this is that generally like the theoretical description is tough, so it's tough to maybe compute it, and like it's mainly through simulations that we extract the data, and of course there's always some kind of noise. Yeah.
Okay, thanks.
Yeah, thank you.
Well, let's thank you again, Simon. So our last speaker is Victor Velasco da Silva from SISSA, Italy. He's going to speak about finite temperature quasi-particle properties of an impurity immersed in the two-dimensional bosonic superfluid.
Yeah. Okay, so hello everyone. First of all, I want to thank you all for staying here that late. I'll try to be as quick as possible so we can now go grab our caipirinhas. So, yeah, the title of the presentation also changed a little bit. So, how do I do here? I'm feeling like an old man that don't know how to use it because it's actually not passing. I'll use here, whatever. Okay. So, so basically, my title also changed a little bit. But basically the same thing. So for those of you who don't know, I'm a postdoc in SISSA in Italy. And this one, yeah, okay, I'm a postdoc in SISSA. And today I'll talk about a little bit of this project that I have been involved this last year, which is basically the study of the finite temperature properties of two-dimensional Bose polar, which is basically the impurity that is immersed in a two-dimensional superfluid in finite temperature. So I'll try to go through the main differences between these Bose polarons in ultra-cold quantum gases, both in 3D and 2D, and try to motivate on why we should study these systems in finite temperature. I'll go through the theoretical modelings that we have used. So basically, we first describe the Bose gas that we have in two dimensionals using low theory. Then we need to add the topological phase fluctuations associated with the vortices that are present in this superfluid. So we use renormalization group to have the BKT physics. And finally, we use what we call this extended T matrix to study the scattering problem between the impurity and the bosons in the system, so the formation of the polaron, and then the results and some open questions that we still have. So basically, okay, not working, so I'm coming here. Let's see, okay. So what are those Bose polarons? So basically, if you have your gas, your system in 2 dimensions or 2 dimensions, whatever, you can create some impurities inside this system by, for instance, exciting an hyperfine state of your atoms. So you create this small population of different atoms inside your system that will behave as impurities. And the formation of the polarons are basically the same thing that we have in solid state physics, where an electron, for instance, that is in a lattice can interact with the excitations of this lattice, which in this case are the phonons, and then you can create a polaron in a lattice system. And here is the same. So this impurity can interact with the excitations of your gas, and these excitations can dress your impurity, creating what we call a polaron, but now in an ultra-cold quantum gas. In our case, it's a Bose polaron because we have a Bose gas. And the nice difference between these lattice systems and the ultra-cold quantum gases is that in gases, the interactions are really tunable by a Feshbach resonance. So you can go, like you can play around with the interactions, which we cannot do really easily in a solid state system. And there are a lot of proposals that the Bose polaron or these quasiparticles can be used as sensitive probe of many-body phenomena in these baths. So it's exactly what we want to do here. We want to use the Bose polaron as a probe of the BKT transition into two-dimensional Bose gas. So let me just go through some of the differences here. So this is a 3D Bose polaron. So we can calculate, for instance, the energy, the effective mass, and the quasiparticle residue of this Bose polaron in 3D. At 0 temperature. And one of the main things that we have in 3D that we won't have in 2D is the condensation, right? So we have Bose-Einstein condensation in 3D, and as we're going to see in finite temperature, we don't have that. But in any case, for the 3D case, you have a lot of different theoretical approaches that can be used to describe this phenomena. For instance, mean field theories, perturbation theory, Gross-Pitayevsky, functional normalization group, and so on. And you can compare with experiments. And you see that when you go like here, like weak coupling, so these zones here for large 1 over K and A, we basically all of the methods agree really well. The problem is in strong coupling. So if you want a nice review of that, you can find a really recent review on all of the physics regarding these Bose polarons. People also went to study the finite temperature properties of these 3D Bose polarons. So you have, for instance, Pfaffian integral Monte Carlo, where when you increase temperature approaching the transition temperature for your Bose gas, your Bose polaron loses quasiparticle properties. So basically, the effective mass, the dressing, tends to become a free particle, so you kill your Bose polaron, basically. There are some other proposals, for instance, variational approach and the T-matrix that we're going to use, where you see not only one solution for your Bose polaron, but you also see the excited states that are associated with the thermal excitations of your system. But overall, the main effect of temperature in 3D is to deplete the condensate, first of all, and the particle, the impurity, feels this depletion. And there will be a competition between temperature and the binding energy for formation of this Bose polaron. Now we go for the more interesting case, which is the 2D two-dimensional Bose polaron. So as I said, the most studies around are for the T equals 0 two-dimensional Bose polaron because it's easier, because we have a condensate. So we still have a condensate in 2D, but only at 0 temperature. And the main characteristic that is going to appear as an important parameter for us is the bound state energy here. Because in 2D, if you try to solve the scattering problem between two particles, for any infinitesimal interaction potential, you're going to have a bound state energy. So this energy scale will play an important role when you compare this with, for example, thermal excitations. And there are a lot of, not a lot, sorry, there are some things in the literature. For instance, here in this work, they use a variational approach to calculate the properties of the Bose-Einstein. So here is the quasiparticle residue, the energy as a function of the coupling. But the open question is how to go forward and how to include the thermal effects here in 2D. So there are, in the literature, we can find two things only, really recent. So from last year, as you can see, one is a functional normalization group analysis, and the other one is a stochastic projected Gross-Pitayevsky equation to solve the problem. We have some problems here because first, the FRG cannot pass through TBKT. We're going to talk more about TBKT really soon. So they cannot overcome, let's say, this temperature. So they don't know what happens to the impurity after the transition or during the transition of the TBKT-like. And for the Gross-Pitayevsky equation, they can only access weak coupling, and they only solve for the repulsive polaron. So they don't go to the attractive side of the phase diagram. So our proposal here is to use a non-perturbative approach, which will be the T-matrix, that will allow us to go from weak coupling to strong coupling between the impurity and the bosons. And we're also going to be able to surpass TBKT. So we're going to see exactly how the quasiparticle properties change as we cross the TBKT transition in 2D. So first of all, we need to describe our Bose gas. So in order to do that, we use this loaf theory. So it's leading order auxiliary field theory, or bread theory, loaf, you know, like that's something like that. And basically, you write down your Bose gas as a 5-4 theory. You do like a sort of, if you want, people are more familiar with like a BCS theory in a field theoretical language. You introduce these two fields. You do a Hubbard-Sartunovich transformation in order to write like an effective action in terms of these two new fields, which we call the density field and the anomalous field. These are going to give rise to some equations of states that one can solve for A and for the density. And the main difference is that when you use this theory, your bath now has an excitation spectrum that is gapped for all temperatures. So this is completely different from the Bogoliubov excitation spectrum that we expect from a condensate state, because there we have a non-gapped spectrum, and we have the phononic behavior at low K. Here we don't have that because in 2D you don't have the broken symmetry state, so you cannot associate this with some spontaneously broken symmetry. So it's you could expect that this system would display a gap. But okay, so here is the behavior of these two quantities. I will explain later the phases. Here is the gap as a function of temperature, and we see that we still, on this level, we still haven't introduced anything about the BKT physics. We're just doing some sort of beyond mean field approximation, but not BKT physics yet. So in order to introduce the BKT, just a small slide to talk about the BKT. So in 2D, as I said, the Mermin-Wagner theorem forbids the formation of a condensate state at finite temperature. So in order to, but even though you don't have a condensate, you have a superfluid state, and the superfluid density in 3D goes smoothly to 0 as you go towards your back critical temperature. And here you have a sudden jump, a sudden abrupt drop of your superfluid density exactly at TBKT. So physically what's happening is that below TBKT you have the formation of your pairs of vortices and anti-vortices. You have this quasi-long range order associated with this algebraic decay of correlations. And when you go above TBKT, your vortices can proliferate freely. And what we want to do is to describe this superfluid density and put this on top of our loaf theory for the description of the gas. And exactly what we did. So in order to do that, we use the Nelson-Koslitz flow equations, the RG flow equations to calculate our superfluid densities, our renormalized superfluid density, if you wish. Our starting point is the mean field superfluid density that we get from loop theory, which is this red curve here that goes to 0 at this line here. And then we solve these equations using this red line as the initial condition. And when you do that, you will normalize this due to the appearance of these topological phase fluctuations associated with the vortices. And then you can see that your renormalized superfluid density gets this huge drop when you cross the NK criterion, which is this dashed line here, this dashed black line. So you see you have this jump at TBKT. So now we are going to, now that we have described properly the gas, okay, so we know that the spectrum is gapped, we know that the superfluid density has this behavior, we're gonna study the impurity problem. And then the impurity problem, we're gonna take this gas that we just described and put an impurity inside of it. In order to do that, we use this non-self-consistency matrix approach that at t equals 0, for instance, you can consider only the renormalization of your contact interactions using this kind of Betzel-Peter equation for your T-matrix. One important thing here that I mentioned in the beginning is that when you do this kind of approaches, you need to renormalize your integrals because they are UV divergent. And you do that by substituting your contact interaction with the bound state energy that is always present in 2D. And then your integrals behave nicely. But these don't capture the thermal effects. So in order to capture the thermal effects, we add on top of the T-matrix a new diagram. This additional diagram basically accounts for the fact that your impurity can interact with atoms that are participating in the superfluid state, and they are also the ones that are excited thermally outside of the superfluid state, sorry. And when you do like this kind of T-matrix, extended T-matrix, you have a new contribution for your self-energy, which is this term here. And then your T-matrix becomes like this as well. And with the self-energy, we are able to calculate all of the quasi-particle properties that we are interested. And these are the main results. So on the top panel, I think it's the most important one, which is the energy. We also have the quasi-particle residue and the dumping. But the point is that when you use this approach, you have two solutions. So we focus here on the blue one and on the red one. Basically, the blue one is the stable solution, which has a sizable quasi-particle residue and a small dumping. And you can see that this solution, as we approach TBKT, given by this line here, you have a sudden jump, a sudden change of energy as we cross TBKT. So this here indicates to us that this solution, this stable Bose-Polaron solution, this stable quasi-particle, is sensitive to the BKT physics that is in the Bose gas that this particle is immersed. The other solutions here are just like resonance-like solutions because it has like a really small dumping, and really small quasi-particle residue and a large dumping, so we cannot associate these solutions with proper quasi-particles. So the main message of this plot is that the proper Bose-Polaron, as you can see, has this change of behavior as we cross from the superfluid phase towards the non-superfluid phase. And our last proposal is to use this Bose-Polaron as a probe to probe the BKT transition temperature. In order to do that, we just characterize the jump of the energy at TBKT. So we made basically the plot of the energy as a function of temperature for different couplings. So the couplings between the impurity and the bosons of the gas is given by this parameter here. And we also did for two different gases, so which are given by these other parameters here. And as you can see, you have this this kind of behavior for the jump. And the most important thing for us here is that if one is able to do a scan of temperature of this quasi-particle, is going to see a sizable change of the energy as the system crosses from the superfluid phase towards this non-superfluid phase. And so just to conclude, so I mean, we have used all of this theoretical machinery to try to solve this problem, which is a non-trivial problem. There are still some open questions that we want to, that we are trying to solve. And one of my last bullet was like experimental realizations of this kind of system are still scarce in the literature. The only thing that I have found was this PhD thesis here, that it has like some sort of energy as a function of temperature, but it's super difficult to translate like the experimental details to something that I can compare with my theory. But today, actually literally today, 6th of November 2025, the group of Parrish and Levinson from Australia, they put this paper on arXiv, where they realize repulsive polaron in the strong correlated regime of a two-dimensional superfluid. So they have some information that may be useful for me to compare with my theory, but unfortunately I didn't have time to read it, so maybe in the close future I will do that. And so I'd just like to thank also my collaborators. Giovanni is a PhD student in Camerino, Perali is his supervisor in Camerino, and Luis Ardila is my main collaborator in Trieste, where I'm working right now. And this paper is probably soon to appear on arXiv. And with that, I finish my presentation. Thank you.
Questions?
So why do you pick the transfer matrix approximation?
Sorry?
Why do you pick the transfer matrix approximation to the
T-matrix?
self-energy? As opposed to like Hartree-Fock or RPA? Like what's the physical reason for this specific diagram?
Well, basically, if you are in a t equals 0 system, for instance, you just like want to do the Betzel-Peter equation with the closed diagram for the T-matrix. You could also use the type of diagram that I have used, for instance, because you have quantum depletion in the system. But since we consider recoupled Bose gases, this depletion is negligible. And then when you go to finite temperature, you need to consider the thermal effects. And this is the most easy diagram that you can add on top of your T-matrix. Like basically, you can try to analytically show that this diagram is important. In 3D is easy because you have the condensate. In 2D is not that trivial, but phenomenologically is what you would expect, right? So the impurity now interacts with the portion of atoms that are in the superfluid state and also those that are now excited out of the superfluid state. So this is, I mean, it's the easiest one that I could think of to try to solve the problem. Okay. Please don't roast me, Nicholas.
So when you talked about regularizing your integral, so basically is it in these diagrams you had, is it the wiggly line that you say has basically the mass of the polaron?
Sorry, can you, I mean, when I do this?
Yeah, this.
Okay, now this is just because when you write these diagrams, you have an UV divergence in 2D. Okay, so in 2D, your integrals diverge logarithmically, and you can renormalize this Betzel-Peter equation here for the T-matrix. You can regularize it, sorry, by doing this substitution there.
Okay, so you're basically saying that this like, I mean, is that a propagator of the wiggly line up there?
The wiggly, the wavy one?
The wiggly line.
Yeah, that's G. That's G, exactly.
Okay, so you're basically saying this boson has the mass of the energy of the bound state.
Yeah, exactly, because the bound state is always present in 2D. If you do the same problem in 3D, the regularization is without EB. So your interaction always carries the information about the bound state. They are connected. So there's a 1 over MA, basically. The scattering length of the scattering problem connects these three quantities. So scattering length, bound state energy, and interaction.
Okay, very cool. Yeah, thank you.
More questions?
Caipirinha time?
Well, as usual, I have...
No, no, please.
Well, I love the enthusiasm. Okay, so I have a simplistic question. So at some point, you had the small n and you had the A, which was at some point, I think your n was the density of impurity, right?
And,
the small n?
No, it's the superfluid density.
Okay, so at some point you had the impurity density. What was that parameter? And,
the impurity
and
density,
also
no.
you had the interaction that you said that you can control it, right?
Mm-hmm,
So can you
Yeah, like this plot, I think, showed the
Yeah.
two things, yeah. So
Okay.
here is this n, little n, is the total density of the gas,
Okay.
okay? I'm working in the dilute regime of the impurity, so we
Dilute
can
regime.
disregard
Which
impurity
is
densities.
distributed randomly among you. And then the interaction of this impurity with the system, that one was in which quantity?
Is in this quantity here. So that's what I told
In
Nicholas now.
A to D,
A
right?
to D is a scattering parameter between the impurity and the bosons,
Okay.
which is connected with the bound state energy.
That's what experimentally they can
Both.
control.
This and that one as well.
These two.
These two they
Okay.
can control experimentally. Yeah.
And this formalism works for the diluted regime, you say?
Yeah, this is in the actually is the single impurity limit, impurity limit. But experimentally, when you have
Single
like,
impurity.
single impurity, yeah. But
Okay.
experimentally, at least for the 3D case, when you have like less than 20% of impurities in your system, the single impurity formalism capture what they see in experiments. So like less than 20% of impurities in the system, it's basically the single impurity limit. So
Okay,
you
but
don't
then
have
there
to.
is no interactions between, well, in principle, you are assuming that there is nothing between the impurities.
Yeah,
No
because you only have
interactions and
one.
all these things.
But if you consider more than one, you can have bipolar formation, for instance, because they can
Okay.
two polarons in the system, impurities, for instance, they can have a mediated attraction between them, mediated by the excitations of the gas. So you
Yeah.
can have the formation of bipolarons, for instance.
And this formalism can accommodate that kind of
You
extra...
you can extend this formalism to do bipolarons. Yes. Yes.
Okay, thanks. And now you can have your
Yes. Like I time,
caipirinha,
guys.
okay.